Hello friends, Namaste. Sorry for some technical problem we had it, but I think now it's all good. So we will take you through on this packaging for space, which is a totally new area we think for us, and we thought in this area of in this age of energy and where the distances are being reduced and new explorations are happening, packaging is also not behind, and it will be good that when our packaging friends know how the things have been happening. So we have attempted to take you historically, and now Gronia will take you through that, this small presentation. Some technical question that you can have, we will open it for the question and answers at the end of the session. You can ask it by unmuting yourself. Right now everybody is in the mute, or you can type it in the question answer session. And now over to Ronnie.
Welcome everyone, I'm Gronia Jain, the presenter of today's webinar on packaging in space. We'll be going over the evolution of food packaging for space missions and discussing different packaging technologies involved. So let's begin. There are primarily two categories that require superior packaging in space. Those are food and electronics. As I just mentioned, we'll be focusing on food packaging in this presentation. To understand the scale of food that needs to be packaged, I'll be going over the dietary requirements of astronauts. On an average, each astronaut requires at least 2,500 calories per day. The calories should be comprised in a variety of foods that provide a balanced diet. The calorie intake is less than the normal 3,000 calories on Earth because in the weightless environment of space, astronauts exert less energy in conducting work. On Project Gemini, food had an average content of 17% protein, 32% fat, and 51% carbs. By the Apollo program, rations were increased to 2,800 calories per day. The main considerations while packaging food for space include the weight and volume restrictions on the flight, microgravity, and lack of adequate refrigeration. To give you a brief, not so brief timeline, between 1958 and 1963, astronauts of Project Mercury tested the physiology of chewing, drinking, and swallowing solid and liquid foods. They ate bite-sized cubes of freeze-dried food and semi-liquids in aluminum toothpaste-type tubes. The astronauts reported that these foods were unappetizing and the freeze-dried food could not successfully be rehydrated. The food was packaged according to Army survival rations. 1961 was the year when Russian cosmonaut Yuri A. Gagarin became the first human to eat in space on his mission Vostok 2. He squeezed beef and liver paste from an aluminum tube into his mouth. For dessert, he had a chocolate sauce, eating it using the same method. Between 1961 and 1966, the dehydration process was improved for Project Gemini, which allowed food that was similar in color, taste, shape, and texture to fresh food to be carried to space. Gemini missions included grape and orange drinks, cinnamon toasted bread cubes, fruit cocktails, chocolate cubes, turkey bites, applesauce, cream of chicken soup, shrimp cocktail, beef stew, and turkey and gravy. That was a lot of options. In 1962, John Glenn became the first American to eat in space aboard Friendship 7. This was the first attempt to confirm that ingestion and absorption of nutrients were possible in a state of zero gravity. Glenn consumed applesauce packed in a tube and xylitol sugar tablets with water, which showed that people could eat, swallow, and digest food in a weightless environment. On 23 March 1965, astronaut John Young carried 2 meal packages to sample on a 5-hour mission. While in orbit, Young surprised fellow astronaut Virgil Grissom with a corned beef sandwich on rye. Grissom, however, did not finish the sandwich because it was producing too many crumbs. Between 1968 and 1972, the Apollo program provided a much greater variety of food on flights. The spoon bowl was introduced, which we will discuss in deeper detail further into the presentation. The storage space for the new thermostabilized flexible pouches and cans allowed for 1 week's worth of food for one astronaut to fit into a pressure-resistant container, which was approximately the size of 3 shoe boxes. In 1973 and 1974, Skylab provided an advanced dining experience due to the addition of a microgravity environment. The supply of food on board was enough for 3 astronauts for approximately 112 days. Collapsible beverage dispensers were also introduced. Skylab relied on solar cells for power instead of water-producing fuel cells, which was a complete game changer. Additionally, dehydrated foods were limited in order to conserve water supply. 1975 was the year that the Apollo-Soyuz test project was introduced. It had a small heating unit on board and meals were consumed in a manner similar to how it was in Apollo and Skylab. During the joint American-Soviet mission, the astronauts dined on Russian specialties such as caviar and borscht in tubes. Quite the growth from eating freeze-dried cubes to caviar, isn't it? Okay, moving on. Between 1981 and 2011, during NASA's Space Shuttle program, food variety had expanded to 74 different kinds of foods and 20 different kinds of beverages. Fresh fruits and vegetables such as apples, bananas, and carrots were first flown on STS-6 in April 1983. Initially, rigid square rehydratable packages were used. However, these proved to be inconvenient on longer missions. To overcome this issue, packages made of lighter, more flexible material with a valve for inserting water were developed and tested on STS-44 in 1991. A trash compactor was also eventually developed to reduce the volume of trash, and new packages were designed to be compatible with the compactor. Without a doubt, food packaged for space needs to be preserved for a longer period of time as compared to on Earth. For NASA's shuttle missions, a minimum shelf life of 9 months is required. For the International Space Station, or ISS, foods require a 1-year shelf life. In the future, the food system for planetary outposts will require a 5-year shelf life because of the planned mission lengths. There are many different types of food and packaging feasible for space. The first one we'll go over is intermediate moisture food. So intermediate moisture food requires preservation by partial dehydration. Enough water content is maintained to ensure the soft texture of the food and no further preparation is required while consumption. Examples include dried fruits like apricot, peaches, pears, and even beef jerky. All of these foods are packaged in flexible pouches. Natural foods that can be carried into space without modification include nuts, cookies, and similar foods. These foods are usually vacuum packed. As opposed to intermediate moisture food, all the water is removed from rehydratable food to ensure easy storage. Water is added to the dehydrated product at the time of consumption. Mashed potatoes and powdered beverages are examples of rehydratable foods carried to space. Thermostabilized foods are heat processed and can be stored at room temperature. They're stored in easy open pull-tab cans and can include tuna, chocolate pudding, and many more. Irradiated food is preserved by exposure to ionizing radiation and is ready to eat. The radiation kills microbes present in the food, but does not make it radioactive. It is packaged in flexible foil and can be stored at room temperature. Chicken, beef steak, and turkey are irradiated before being carried to space. Refrigerated food, as the name suggests, needs to be stored at low temperatures. Sour cream and cream cheese are two very obvious examples. Fresh fruits and vegetables are rinsed in 200 parts per million chlorine, air-dried, and placed in the food locker tray. The on-orbit shelf life is around 2 to 3 days only for most fresh fruits and vegetables, when there is no refrigeration. Research is continuously conducted to address odor control and provide better storage that can inhibit metabolization. NASA suggests testing controlled atmosphere packaging, similar to MAP, for this purpose. Let's go over some of the packaging designs traditionally used and what might be some inherent problems with the same. Tubes containing food were designed with a small straw attached to the opening. This allowed astronauts to squeeze the contents from the tube and use oral suction to pull it directly into their mouths. Special materials were also developed to coat the inner surface of the aluminum tube to prevent formation of hydrogen gas. Hydrogen was usually formed as a result of contact between the metal and the acids contained in certain foods, like applesauce. Since the weight of this aluminum tube tended to be more than the food contained in it, it was soon replaced with lightweight plastic containers. Initially, compressed, dehydrated solid food was processed in the form of bite-sized cubes, which would be rehydrated by saliva as the food is chewed. However, it was noted that small particles from these cubes floating in microgravity could possibly damage equipment or be inhaled. Thus, these cubes were coated with edible gelatin to reduce the chance of crumbling. The cubes were vacuum packed in containers that held the quantity of an individual serving. The containers were made of clear, 4-ply laminated film plastic. This packaging design prevented the food from spoilage, moisture, and loss of flavor. The image on your screen shows the original packaging from Project Mercury. You can see the cube-shaped, bite-sized rehydratable foods and the aluminum tube. Next is freeze drying. So freeze drying is beneficial for carrying food on space missions because it's a lightweight option, provides long shelf life, can be stored at room temperature, and now closely resembles original food in taste and texture once rehydrated. To prepare a package of freeze-dried food, the food is first sliced, diced, and sometimes liquefied to reduce preparation time. Post-cooking and then processing, it is quick frozen and put into a vacuum chamber on drying trays where air pressure is reduced and heat is applied. That happens through heating plates. At this high temperature and low pressure, any ice crystals in the frozen food boil off and the water vapor generated is condensed to ice on the cold plates inside the vacuum chamber. This whole process is called lyophilization. During the process, only water and no essential oils and flavor are removed. Let's focus on the inside of a freeze dryer. There's a vacuum pump along with a refrigeration system containing a condenser. There's also a heat source that allows evaporation. This is what food products usually look like once they come out of a freeze dryer. To rehydrate freeze-dried food, initially water was injected into packages through a water gun with a fitted nozzle. Later, the nozzle was replaced by a valve. Aboard a space flight, hydrogen-oxygen fuel cells provided the source of water. At the other end of the package, an opening is designed through which food is squeezed out for consumption once rehydration is complete. An area of concern had been the limitation that the size of the opening puts on the size of the food particles that can be extracted at one time. Once the meal is done, germicidal tablets are filled into the empty packages to inhibit microbial growth. By 1968, something called spoon bowls that we discussed in the timeline were used to package rehydratable food. Spoon bowls are basically made out of plastic, and a pressure-sensitive plastic zipper is used to keep the food inside the container. For consumption, water is injected through a water gun and then the zipper is opened. Food is extracted simply with a spoon, like on Earth. These are spoon bowls from the Apollo mission. You can see in the image on the right that an added seal that needed to be cut open in addition to the pull-apart zipper was included into the design to ensure that the zipper can only be opened intentionally. Currently, NASA packages both rehydratable and bite-sized foods in Combitherm Paxx packaging materials. These packages are made from a 5-layer co-extrusion of nylon, ethylene vinyl alcohol, tri-layer of polyethylene, and linear low-density polyethylene. For bite-sized foods, NASA procures packaging sealed on 3 sides from a vendor. The food is added and the package is sealed on the 4th side. Rehydratable and bite-sized foods are packaged using modified atmosphere or MAP techniques. This means each package is flushed with nitrogen 3 times before the final seal at 21 to 29 inches of mercury vacuum. The amount of vacuum used varies depending upon the food product, as a hard vacuum will destroy the texture of some delicate food types. Another type of packaging used for rehydratable food is the Rehydratable pouch with Septum adapter assembly. This packaging allows food to retain moisture when water is added and is made of flexible material to aid in trash compression. The material composition includes polyamide, ethylene vinyl alcohol, and polyethylene, very similar to the Combitherm Paxx packaging. When rehydratable packages are procured from the vendor, they come in the shape of a cup and a lid. The flexible cup is formed by thermoforming the 5-layer co-extruded film over a mold. The thermoforming process does decrease the barrier properties of the original film, as the material is stretched thinner to form the cup. To package, NASA places the food product in the cup, places the lid on top, and seals the lid. The septa of the septum adapter assembly is made from silicone rubber and is inserted into the septum adapter with a special tool. This septa provides the entry for a needle that injects water into the package for rehydration. The septum foil laminate seal is pierced by a galley needle to initiate rehydration. It is sealed off when the needle is withdrawn. The adapter is made of LDPE and PET. Moving on to thermostabilized food. Wet packs are thermostabilized, flexible, also called retort, pouches made of plastic and an aluminum foil laminate, which retain the water content of the food. This type of packaging is the American preference for thermostabilized food. The Russian preference is to store it in cans with a full panel pull-out lid. Thermostabilized food was first eaten in space on Christmas Eve 1968 aboard the Apollo 8. The astronauts opened their meal packages to discover thermostabilized turkey with gravy and cranberry sauce that they could eat with a spoon. Retort pouches were originally modeled for the Meals Ready-to-Eat program used by the U.S. Defense Department. They're made out of PET, biaxially oriented nylon, aluminum foil, and cast polypropylene. NASA's Beverage Package is a modified, longer version of Capri Sun package made from a foil laminate. Beverages are packaged for spaceflight by following certain steps in a specific order. First, dry beverage powder is placed in the package, then the package is flushed 3 times with nitrogen, and lastly, the septum is inserted and the beverage package is sealed. Overwraps are sometimes added for additional protection and to increase longevity. They're all made of PET, white LDPE, aluminum foil, and Cerlin, but vary in sizes. Okay, some more interesting bits coming up. We'll now talk about some accessories and technology used in current times. Hot water guns were first seen on Apollo and provided both hot and cold water for preparation of food, unlike before. Food restraint pouches are used as a tether for the food while rehydration and eating. Small Velcro tabs are attached to it that enable the food to be fastened to the spacecraft to prevent it from floating away. A contingency feeding system was first carried on Apollo 11 in the case the spacecraft cabin becomes depressurized. In that case, the astronauts would have to always be in their spacesuits and thus would not be able to eat solid foods. The system allowed astronauts to eat liquid food through a small port in their helmet. Starting with Apollo 13, a canteen was added to the astronauts' spacesuits that allowed them to drink while they worked on the moon. The Apollo 15 astronauts carried apricot food bars in this form for a snack during increasingly long work periods on the lunar surface. Starting from the left, here are some examples of packaged food on Apollo missions. Pineapple fruit cake, which required no additional preparation, peaches that needed to be rehydrated, beef and vegetables that required rehydration with hot water. Freeze-dried chocolate pudding, powdered tea that required rehydration, and compressed brownies that can be eaten directly from the bag. A few more examples include dehydrated and compressed beef hash, spiced fruit cereal that can be stored without refrigeration and be easily consumed in weightless conditions. On the International Space Station, food needs to be stored for longer, and packaging is usually made of polyamide, polyethylene, and ethylene vinyl alcohol. Food is stored in easy pull cans, plastic cups, and sachets. Most Russian food is dehydrated or thermostabilized or has intermediate moisture. Unlike NASA's food, packaging still includes metal tubes, cans, and plastic overwrapped in foil. Russian cans are made of steel and require a can opener and come in 2 sizes. Freezers, refrigerators, warming trays, and stationary tables were put onto space stations since the creation of a microgravity environment. Food was then packaged in specialized containers. Rehydratable beverages started coming in collapsible accordion-shaped dispensers. Other food was packaged in aluminum cans of different sizes or rehydratable packages. Before consumption, the food packages are placed into warmer trays that heat food during the spaceflight. Many different technologies and equipment are used to adequately prepare food for space. These include test kitchens to develop product concepts, freeze dryers, retort machines, pilot scale production equipment, canning and pouch sealing equipment, temperature controlled storage for shelf life studies, some analytical testing equipment, and a sensory evaluation center. At NASA, packaging weight for a shuttle program is usually around 0.5 pounds per person per day. The weight of packaging waste for food on ISS is much greater as rehydratable and bite-sized foods are packaged for the shuttle program are overwrapped with an aluminum foil laminate to increase shelf life. Thermostabilized pouches are used more on the ISS, which also adds food package weight and waste. A design requirement for wrappers and empty packages of all foods is that they must be compressible to minimize the amount of trash on the spacecraft. There are very few opportunities to get trash off the ISS. In fact, trash is disposed of only when space vehicles such as the Space Shuttle, the Soyuz capsules, and other cargo vehicles visit the ISS and then depart. This happens about once a month, and even these vehicles have limited amount of space available, so trash must be as compact as possible. Any new food or packaging types are only introduced on the condition that they minimize crumbs, packaging and trash volume and weight, are nutrition rich, and can be easily prepared. Longer shelf life for longer missions and the ISS is also preferred. Some research questions for further development are on your screen. How does space radiation affect the nutrients in food over a long period of time, and how can packaging prevent or delay any degradation? How to preserve the joy and comfort of eating like on Earth for missions that span multiple months or even years? How can medicine preservation and consumption improve in space? Something to really think about. That's all that I have for you today. I will hand it over to Mr. Goyal now.
So hello friends, can you hear me now? Okay, so I hope you like this presentation, and this was our little attempt to come to the new area, how things are happening above, which we really don't see. And you can see that not much different except the microgravity environment and some challenges, but the basics of the packaging are same, and the vacuum is very much used with the oxygen barrier. So if somebody has asked me the question, and 1 second before we go further, I will unmute you all. Yes, now you all have been unmuted from the dashboard. So if you want to ask any questions, you can unmute yourself and ask. And in the meantime, you can answer. Yes, tell me. Somebody wants to ask a question? Okay. So somebody was written a question that space with PP, PE, and EVOH. Yes. And in fact, the EVOH is used for the oxygen barrier, but at the same time, nylon is also used because it gives a very strong puncture resistance. And because vacuum is there, so they go for the extra safe. So the combination of nylon, EVOH, and with PP and PE is used. And more things are happening, but you can see the lot of flexible packaging is heavily used over there. And the key thing is that it should not do too much of trash. Otherwise, easy we can do a lot of overwrap and a lot of extra packaging. But when you're on this space, every gram matters because expensive fuel, every gram is a critical thing. So the weight and the volume of the shuttle is very, very important. So we cannot just overpack it. Now the question is why is CPP used in retort pouches? Yeah, CPP is used in retort pouches because it does not deform when you are retorting it, and it keeps the shape and no degradation happens in general with the PP family, and CPP gives you the good results, good strength and good sealing, and seal also does not break when you do the retort at 121 degrees. So what we will do in addition to what we just did this packaging for space, we are also into many other areas working on the different packaging consulting project with FMCG and pharmaceuticals and the different area designing, etc. And we are also working with many European packaging companies to bring them to India, and also helping companies to roll out new packaging concepts globally through packagingconnections.com or through such webinars. We will send you those details or the link of the presentation in a follow-up email, and you can then download and you can write to us or whatever. You can reach us anytime. This presentation will also be available on the YouTube, and you will get the link after we finish this session. I think by tomorrow you should be getting it. Till then, we wish you a great day ahead, and thank you very much. Bye.